Welcome back, physicists, and coming at you live from Ted Stevens International Airport. I would like to remind you that Ted Stevens is a smoke-free airport. So, here we go. Looking at Chapter 8, we are going to finish it up completely today. In our last section, we were looking at things like torque and how net torque makes things in equilibrium, or can at least, and as a result we don't get movement, just like we saw with net force. Now, the ladder problem, I think it was the ladder problem from your assignment is kind of ugly to work with, but I just want to stress, reach out if you have questions, concerns, anything like that. So let's not waste any more time here and just get down to the deets. So in 8.3, we are continuing on, and I'm going to make that a little bit more bold. We are in 8.3, and if there's noise in the background, I apologize, but I'm unable to fix it because, airport. So here we go. 8.3, we are continuing on from yesterday where we were looking at net torque and all those ideas. So today we're just going to take a little trip that's a heck of a lot less mathy, but equally as interesting, one could claim. So 8.3, we are going to jump in today, and our first topic that we're going to cover is rotating frames of reference. Cool. So we have some rotating frames of reference that we're dealing with. And it turns out we actually live on one of these big rotating frames of reference, and we have to account for that when we do a lot of stuff, on this beautiful planet. But we're going to jump in, and I want to introduce a couple little assumptions. When we use the term merry-go-round, there's a few versions of this, but we're going to think about the crazy awesome version that you've probably never even considered. So a couple things, we're going to use the merry-go-round as a pretty common example in here, and because that, I'm going to go ahead and recommend that we call this MGR. Cool. So anytime you see MGR, it is indicative that we're talking about a merry-go-round. Now, beyond that, if we were to draw a merry-go-round, and I am not great at drawing these, I want us to imagine a little bit different one. So here's a regular merry-go-round. You don't have to draw this. I just want to think about it. And there's probably some post here, and it comes out of here, and there's little handles that you can grab onto so that you don't flail off into oblivion. I like that. I'm good with it. However, I want us to imagine, whenever we're thinking about these things, that they're actually huge, and more than that, they have walls that encircle them, and the people inside riding on it, they can see each other. It's light. It's a magic merry-go-round, but they don't get to see anything moving outside. That is important because when we're trying to connect these ideas, our experience with merry-go-rounds leads us to maybe have some misconceptions about what's going on within the realm of physics and these ideas. So here we go. Just start us off, we're going to work on a nice, lovely merry-go-round, and here it is, and I'm looking at it from above right now, and we have some sort of angular velocity. Remember, that's omega, represented in radians per second or degrees per minute, revolutions per minute. Doesn't matter what the unit is, but it's turning. And hypothetically, let's say that we put a rock right here, a little bit off center, and this thing is turning. Now, if we turn it fast enough, naturally, and this is a good questioning thing that we could do in class, but I'm not there. So if this thing starts turning, or is turning, and we set a small pebble on it, I don't think it's a big stretch to say that, hey, that pebble is going to eventually push its way off. Now, here's the weird thing. There is no true force acting on this pebble. So I'm going to indicate here pebble, and we're going to make a little comment to start off. Right off the bat, just want to make it really clear. A pebble that's moving to the exterior, like is going on in this, has no true force acting on it. There is no real or true force. There's no agent that causes it. It's motion that causes it, but there's no agent to cause it, so there's no real force. Now, with this, we get into this kind of conundrum right off the bat, because if we are sitting here and we're observing this happen, I think that it's really counterintuitive to agree with this statement, because Newton tells us that, hey, if you apply a force to a mass, it accelerates. Okay, baggage should be attended at all times. Now, with that in mind, the fact that there's no real force, there's a little caveat to Newton's laws that we don't often discuss, at least until we get here. Newton wasn't wrong. What's really going on here, and this is just a small follow-up, what's really going on here is when we think about that idea of force equals mass times acceleration, Newton's laws don't apply in certain situations. Now, specifically, we're in one of those situations right now. They don't apply with rotating frames of reference. Which means if you're sitting on something spinning and you're trying to use Newton's law, good luck. It will not work, because it doesn't work when we have a rotating frame of reference. Now, just to clarify a little bit further, I'm not indicating or stating that Newton's laws can't be used to talk about rotation. They most certainly can, and we will, but when we view it, you can't be spinning along with the object. That's a big deal here. Now, furthermore, we don't work with Newton's laws in accelerating frames of reference either, or points of view, however you want to think about it. And if you think about something spinning, it spins because it's accelerating toward the center. Remember that centripetal acceleration idea. So there's kind of the premise of where we're starting, and let's go ahead and kick forward. There are two primary types of quote-unquote forces that we're going to deal with, and they're really kind of two flavors of the same idea. And the first of these is what we're going to call and define for ourselves as a centrifugal force. Now, when I think of a centrifuge, I think of one of two things. I think of either spinning vials of blood to separate the plasma, thanks to the centrifugal force, or we think about refining nuclear materials. In either situation, the air quotes are certainly appropriate when we talk about centrifugal force. So, just by definition, we're going to say that centrifugal force is just the apparent force. And again, I'm going to use those quotations. It's the apparent force that one feels while in a rotating frame of reference. So if we are sitting outside the merry-go-round watching it spin, we don't feel it. But somebody sitting on it who is within that frame of reference it's spinning, they do experience it. So apparent force one feels while in a rotating or turning, spinning, however you want to word it, frame of reference, or reference frame if you'd rather. Okay, so here we are. We have this idea of this quote-unquote force. Now, as we look at this, we're going to look at the same situation from a couple different points of view. So, first off, I'm going to have two different images that we're going to use to think about this. And they're both the merry-go-round. We're just going to view it from different situations. If we have a spring that stretches out, and I connect one end of it to the very center of my merry-go-round and put a mass on the other, and it starts to spin. As we spin faster and faster, what happens? And I know it's rhetorical because I'm not there with you right now, but if you talk with your neighbors, go ahead and tell each other, volunteer who goes first, just what happens if we have a mass connected to a spring and we start spinning a merry-go-round with it on it. So as you're discussing, I'm going to go ahead and start getting some stuff set up. All right, so here's the cool part. I think we can all agree that what's going to happen is we're going to see that object at the end of the spring start to stretch out because the spring's going to get pulled by this quote-unquote force, and that's like the biggest thing that we're going to realize. So right off the bat, I'm going to say that, hey, first view, let's do a fixed point above. So we're not on this. We're looking at it from above. We're not spinning. It is spinning. So if we give ourselves a lovely merry-go-round, and right at the center we have a spring connected to it, and I'm not going to draw the spring, but let's say that I have a spring connected to it and it's been stretched out, or it's starting, and let's say it starts here and hypothetically we'll go this way with our alpha, or sorry, our omega. If this is the first point in time, then the next point in time it's going to be a little bit longer, and a little bit longer, and a little bit longer still, and a little bit longer still. Now, in this situation, eventually we're going to get to the very longest that this thing can be, and this is what I want to think about. There is nothing that's physically pulling on this object, right? Like there's no magic force or unseen field force like gravity or magnetism. It is acting on its quote-unquote own here. Now, from our perspective, if we're watching this from above, it is super clear that this thing, even if it's at constant velocity, is undergoing centripetal acceleration. So we'll say from here, or from above, because that's where our fixed frame of reference is, from above, it's clear that centripetal acceleration is at work. Now, what I mean by that is, if it weren't, right, this thing would just fly off. It's like we cut the spring and that linear velocity just continues on. So there's very clearly centripetal acceleration. And it would be a shame if we talked about centripetal acceleration without making sure that, we hit a little bit of the math and review stuff. So, quick little connection here. You may not recall off the top of your head, but we have centripetal acceleration. And as discussed earlier, it can be calculated using the square velocity over the radius. So all fine and dandy. This acceleration, remember, points toward the center of the circle, and we'll keep that in mind. Now, we can use this idea to go just a little step further. And with that, I'm going to say one more little piece where we had a nice connection where we connected linear and angular velocities, where we wrote this statement last week, I believe. Velocity is just the radius times the angular velocity, omega. So this is our connection between linear and angular. Now, if we keep kicking and we just do a little bit of substitution, what we can find is that, well, this value of velocity can be substituted right here. So we wind up with the expression that centripetal acceleration is r omega squared over r. So just a little bit of substitution here. And we're nearly there. One more little step. I get r squared omega squared. That's by taking r omega times r omega divided by r. And fortunately for us, we get some r's that wind up dividing out. And we are left with the following. Centripetal acceleration, the force or the acceleration that causes this thing to keep moving in a circle, or worded differently, that fights the inertia that wants to keep it moving in a straight line, is exactly equal to the radius times omega. Okay. Now, as we deal with this, here's what we have going on. As my speed, my angular velocity increases, so as my merry-go-round spins faster and faster and faster, as this happens, two other things must also increase. Right off the bat, we see that as this happens, the acceleration toward the center, or the centripetal acceleration, must also. Okay, so we have a larger acceleration that's acting on the same mass, and all of a sudden, check this out. If this acceleration increases, well, then so must the force that's pulling it, or the force in the direction of this acceleration. I'm going to say AC, or centripetal acceleration, must also. And not only that, but the centripetal force that we feel, or that the slinky or the spring feels, whatever it is. Now, when we look back at our circular motion, we used tension over and over and over, because it's tension that produces this centripetal force that pulls us in. Now, as we apply larger and larger tensions, because we have to pull towards the middle harder, we get a spring that just stretches out. So there's a connection here that we can see that, hey, nothing magic is happening. We're speeding up, which means we're accelerating centripetally, which means our force must also increase. So nothing crazy there. Now, there's nothing wild about this. If we're looking from above, I hope that this makes sense. If it doesn't, please reach out to me, talk with your neighbors, ask to pause the video if need be. I'm cool with all of those things as long as the end goal is making sure that this idea clicks in your head. So just to keep things nice, I'm going to write FC right there, since that's, I believe, all I had on this line. All right. So we've looked at our merry-go-round from above, and we've identified that, hey, this thing's spinning, and centripetal acceleration is what causes this circular path. And we work out all this math and make this big connection. So transitioning, let's go ahead and do things a little bit different. So instead of sitting above this merry-go-round, or our rotating frame of reference, we're going to be on the merry-go-round. And it's hard to imagine when we think about this, but again, I want us to think that we can't see the outside. Maybe, just maybe, we're turning slowly, although the spring's not going to stretch really far. But here's the big connection. We can't see it. We're ignoring everything else going on around us because we can't see it. Now, it's possible that as we sit inside this closed little piece, we are unaware of the circular motion. If we can't see movement, and we can't see that we rotate, or the spring in that situation, we can't tell that it's rotating because from our perspective sitting on it, we're rotating with it, and if we were at the right spot, all we see is a spring stretching out toward us, and it seems like it's magically happening. But it's not, right? Because we just saw that from above, it is rotating. But inside, we can't see it rotate, which all of a sudden, this leads to us being unclear. And let me straighten this out. We can't identify, and this is that unclear statement, we can't ID or identify what this unbalanced force is caused by. Because if we don't see that there's centripetal acceleration, then there's nothing that we're expecting, like suddenly it's pushing back against nothing. So we can't identify what this is caused by. Now, I want to stress, and I made this comment before, but there is no force. All that we're really seeing as this spring stretches out is not a force. No force pushing or pulling the spring. But instead, all that we have is inertia. The tendency to keep moving the way that you're moving. It is the inertia of the mass that's connected to the end of the spring fighting the centripetal acceleration. That's it. And I'm going to use A sub C for centripetal acceleration. It wants to keep going straight. It's being forced to not go straight. So unlike a string or a rope that might snap in this situation, we get to see our spring simply stretch out a little bit further. Now, this idea can be used, and it is used all over the place in our modern world. So the easiest place to look at this, and we're going to view two different ideas here. The easiest place in my mind to really think about rotating frames of reference is our last couple little pieces of the chapter. First off, we're going to talk about what is called the Coriolis, and I'm going to call it a force in here with quotations. The Coriolis force. Now, turns out the Coriolis force is exactly what causes things like wind and why when we fly on planes we take these weird curved paths. It is due to the fact that we exist on a planet, right? It's Earth, and our planet is constantly spinning. So we're on this rotating frame of reference that for most things that we do, we can ignore it, at least in our course, but it is there and we are turning and we don't feel it. Like we're accelerating right now centripetally, we have no recollection or don't even gather it at all. However, Let's work with that large and fairly slow moving merry-go-round that we can't see outside. And I want us to consider two things. We are going to have two people on each side. So we'll say two people on opposite sides of a merry-go-round. And it's a gigantic merry-go-round. Cool. Now, I want to look at two situations. We have two people on opposite sides, and they roll a ball. Or one rolls a ball to the other. One rolls, or throws, but rolls is easier, a ball to the other. Okay. So, in this situation, we are going to look at first the nice normal situation without movement. So here's person A and person B. And assuming that person A can aim, I'm going to go ahead and just say this is 0 radians per second. If this person can roll really well, when they roll a ball, even from their viewpoint, from my viewpoint, doesn't matter, this ball moves straight. Now, this is not a surprise. However, if we look at this situation and all of a sudden we start to move it. So we're going to kick it up a notch, and all that we're changing, same merry-go-round, same two people, but all that we're going to change here is we're going to give this thing a little bit of angular velocity. So at this situation, we need to be able to track some changes. So theoretically, let's say we have person A at A1 and person B at B1. And we let a little bit of time go by, or a lot of bit of time, and we wind up at A2 sitting here and B2 sitting here. So all that we've seen is this person has turned this direction. Cool. Now, if this person were to roll the ball here, and I'm like, don't draw it all until we can commit to it, but they roll the ball, and it rolls and rolls and rolls, and from our outside perspective, maybe it still looks like a straight line. But for that person, when the ball gets to the other side, instead of sitting here and seeing that it rolled in a straight line, they're sitting here, and a straight line across the circle would wind up like this. So it looks like their path, that ball must have curved this way. And it didn't, right? Like, it's only from their perspective. When they roll the ball here, if the person A at A1 aims at B1, they're going to miss B1, because by the time the ball gets over here, that person's going to be up here. And it looks like a curved path and things are wonky. But here's the weird part. From person A's perspective and B, the ball seemed to drift. Like, it seems like it's a curved path. And from their perspective, it is. They are correct about that. But from our perspective, in our non-rotating frame, I think we would see something different. Even though person A1 or A1 moved to A2, the path of the ball is still the same. It's their perspective that has changed. They've had to look at it from an angle that they weren't at before, because motion wants to stay unchanged. That's the whole idea of inertia. It wants to keep doing what it's doing. So, as we look at this, what it winds up being is the curve ultimately is just an illusion that is entirely caused by the fact that they rolled it from a rotating point. Okay, these ideas are awesome, and they're weird to think about the first time. There's no real agent causing this drift. It's a perspective issue. Cool. So one more little tiny piece, and we're done with it. Where we care about this, and why I think you should care about it, and maybe you don't, please don't tell me, but why we should is, turns out this matters to us. This is the only course that I've ever taught where I see Coriolis presented as a force. In other courses where you might see this, things like Earth and Space Science, marine biology, oceanography, pretty much every other science apart from physics and probably chemistry. But if we look at Earth and Space Science and you encounter Coriolis, you're not going to encounter the Coriolis force. You instead are going to encounter what is called the Coriolis effect. And this is much more common of an idea to present it as, because we live on this big rotating ball, right? Like we're this big spaceship flying through space and spinning crazy fast. So as we're looking at the Coriolis effect, we are going to do a little bit of fancy art. So check it out. Here is a wonderfully awesome Earth. And to give it a little bit of, depth, we're going to add an equator, which exists at, we'll call it 0 degrees. And assuming that this up here is the North Pole, that's north, and down here it'd be hidden from the perspective we're looking at. We have a North Pole and a South Pole, and the Earth is spinning. Now, if you weren't aware of it, the Earth, and if you've never thought about it, and I think we did it in this class, but I could be confused. The Earth rotates, if you're looking at it from this perspective, the Earth rotates this direction. Now, that's a weird statement to make, and we'll talk about why that's so weird, because it really just depends on your perspective. But what I see is the easternmost point on Earth crosses my line of view before the next western point. Spins to the east if north is up. Anyway, I want to make sure they have a few facts. First off, from above, so we'll call this fact. Okay, first fact was the one that I just highlighted. From above, or if we were to look down at the North Pole, from above is what I'm going to refer to that, because we all think of north, I assume, as being up. From above, Earth spins counterclockwise. Cool. So it's just like the unit circle, and we work through angles all the same way. Beyond that, we're going to pretend as though we're doing a nice little MRI of our planet. And I assume we've talked about it in here, but this statement I will clarify with, you don't have to draw the picture, but if we were to follow lines of latitude all the way up, what we wind up seeing is if we were to take out just one little tiny line of latitude and took a cross section of it and looked down, we would see a circle. And as we work our way up from 0 degrees to maybe this next line of latitude to maybe up here, we just get a bunch of circles. Now, an important observation about that circle is that as latitude increases, the radius at that latitude decreases. And it can be kind of hard to tell from this picture, but assume that I was able to somehow just cut out a bunch of little pieces here. So here's the first little piece that I can see that, oh yeah, it's a circle. And then down here at maybe 20 degrees, whatever it is, I get another nice little circle living here. And finally down at the equator, we get a bigger one, and I could do this however many times I want. But I get a bunch of little discs that I'm looking at. Now, on any of these discs, doesn't matter which one it is, if I were to take the radius here, and I compared it to the radius here, and the radius here, my hope is that it's pretty clear that we're seeing this statement. Radius gets smaller as we move up. Okay, now we're going to use this idea, and we're going to formalize this a little bit more in the process. If we travel north from the equator, so I'm going to draw another Earth here, and this time I'm not going to make it three-dimensional other than I'm going to put that. If we travel from this point and we head due north, which points toward the pole, or I'll even pick right in the middle so I can just go straight up. I can't go from this point to this point instantaneously, which means if I start here and I start traveling, I'm going to see that as I move up, the radius gets smaller. But not only that, the initial linear velocity that I had at the equator in this situation is much larger because, as we saw before, I know that linear velocity is r omega, so the bigger the radius, the faster the linear velocity. So here we go. As we move north, we bring the big angular velocity, which I'm going to say big, from the equator. We bring that big angular velocity with us to a point on the planet, and I'm just going to say a point with a smaller radius. Now, if this idea feels comfortable with you, let's say in 1 second at this speed, I can follow this path of this arc. Maybe I go that far. Or 1 minute, 1 hour, whatever. If I go the same 1 minute here, I need to go the same angle, but my linear velocity is way, way higher. Okay, as we're looking at that, remember, linear velocity is RW, and, way smaller. As I look at this, I'm going faster than the Earth is because I'm going faster here, which means if we're in the northern hemisphere, what winds up happening is if I head to the north, my horizontal direction here and here is larger than we expect it to be typically, which means we get a path that ultimately deflects like this. Now, the same is true. It's because we have a higher velocity towards the equator than we did up here because of the size of the circle we're traveling on. Now, in contrast, or let's summarize this. As we move north, we bring the big with us. We bring the big angular velocity to a point with a smaller radius, which means we change colors on accident. We move ahead on Earth. And what I mean by that is ahead in the positive direction to the right, which is our convention. Now, in contrast with this, if we're up here and we start working south, it means our radius is getting bigger, which means, well, gosh, my angular velocity is still the same. So if my angular velocity didn't change, well, then something else must have. And it's my linear velocity. So I'm here and I deflect this way. Okay. Now, it happens if we're going north or south. I deflect to the right if I'm going further away from the equator, or from a person's path, they deflect to the left if they're going closer to the equator. And if we generalize this and just put a nice line here, we're going to use that same idea. Getting further from the equator, I go to the right. So if a person's walking down the planet right here, from their perspective, they're going to go to the right. So let's see, their perspective, they're going to go walking down, there we go. And I'm getting goofed up here. They're moving slower than the Earth, so they wind up behind where they should be. There we go. If you're walking north in the southern hemisphere, your path deflects to the left. If you're walking south, it does the exact opposite and deflects this way. Cool. We have all this linear velocity from the equator that gets carried with us, and all of a sudden it looks like we're traveling faster due to the rate difference of the circles that we're traveling on. Now, without going crazy with this and just a little skosh, just a little tiny bit of meteorological science or atmospheric science, this turns out is a huge it's a huge cause and the driving force, one of the major driving forces of the winds on our planet that, help do some pretty cool things like spread culture around the world once it was developed. This part, I don't necessarily need you to write it down. I think it's awesome to have, and you're going to look like a smarty pants at some point if you do and you remember it, but I do want to talk about it. On our lovely planet, we get some sunlight. Now, I'm not going to go into the whole science of it, but it turns out that if we track out a couple degrees of latitude here, so here's our equator, and then let's say here's 30, 60, and 90 would be all the way up here. And we could do the same thing in the south, but I'm not going to label them. It turns out, for reasons beyond the scope of what we're talking about right now, something on our planet happens that brings winds and brings air masses down like this, toward the equator, due to other causes. Now, when this happens, all of a sudden, we get this Coriolis effect acting on us, or acting on the air mass. Each of these air masses winds up deflecting toward their right. Now, in the southern hemisphere, we get the same things happening. We have wind that, for some reason unknown to us, starts pushing up toward the equator. And because of this Coriolis effect, we get the same thing. We get winds that start to veer to their left. And all of a sudden, if we did this all the way around the planet, it looks like we have winds that blow from east to west all around like the tropics, which is pretty handy if, you're a person that lives somewhere near the tropics and you want to go from, I don't know, northern Africa to Central America. You can ride these winds the whole way through. Now, again, it's not our focus in here, but if we keep working up, there's another driving force on our planet that pushes between 30 and 60 degrees the air north in this northern hemisphere or the air south in the southern hemisphere. So, similar idea. We have things that are moving to the north and they're going faster than where they end up, which means it looks like their paths wind up deflecting this way. In the southern hemisphere, we get the exact same idea. It just flips direction. So we're going south, we deflect to the left, and here's a whole new global wind pattern that, allows people like, I don't know, Northern Europeans and the Vikings to maybe sail their boats to Greenland, Iceland, Newfoundland, all of those places. There's one more that exists, and it works out really nicely. We're not going to do the same thing, but we get winds up here that all of a sudden start turning the same direction again. So we have the trade winds that exist here. We have our westerlies that exist in the 30 to 60 range, and then we get some polar easterlies, where, again, not our focus, but when you're talking about wind, it turns out that, lost my train of thought, I'm sorry. The direction that they come from is how we talk about it. So a northerly wind brings cold for us, because it's bringing air up from the north, which is typically colder than where we live. So this is the end of our chapter. What I would like you to do, and I need to check the Google Classroom to verify that I'm going to tell you the right thing. I was going to use this simulation to work through stuff, but unfortunately it didn't work out for us. So here we go. In physics, for Wednesday, it looks like Wednesday, March 5th, we are continuing on from the assignment from yesterday. Now, we will talk about this. For sure we will talk about this because these ideas are pretty complex, especially the first part of the chapter. But I want to remind you that everything from this week while I'm out is due this Friday by 11:59 p.m. And I think I hooked you up. So if you scroll down just a skosh, if we're looking at 8.3, here are the problems. This problem is challenging. Number 41, I think, is especially challenging, like a legit challenge compared to most of them. And then if you just go through a little bit, here are the questions at the end of the section as well. And I'm trying to zoom out. I can't get it to show you everything. I'm going to try. Boom. There they are. Cool. So if you're watching this on the road, there are your problems. Your assignment for the second half is to work problems 42, and I lost my spot. 42 through, I assume it's just all of them. 42 through 48. So for each half of this, and they can be on the same page as long as you take pictures of specific problems, I need it submitted to the Google Classroom. Can't stress it enough. At lunchtime, take a picture, submit it, you're done. Cool. So tomorrow in class, so Thursday and Friday, you guys are going to start looking at the study guide. Now, looking at this, you're going to work on that Thursday and Friday, and I completely understand and empathize that you probably have some other stuff going on. So when you finish, if you finish, great. But if you don't, I don't want you to stress, because as long as Ms. O'Malley can confirm for me that you guys are working diligently in class, I want to talk about a lot of that when we come back from break the following week. Cool. So, as always, please reach out with questions, and Holloway out.